So let's take a look at a summary of Chapter 16 Vector Calculus and sort of review all higher dimensional versions of the Fundamental Theorem of Calculus that we have learned in this chapter. Now, if you've watched all my videos, this is where Calculus 3 ends and where most calculus classes stop. Now, in Chapter 16, we basically learned 4 main theorems here, as shown on the screen, which are all higher dimensional versions of the Fundamental Theorem of Calculus. So basically what I want to do in this video is review by writing out all 5 of the formulas, grouping some of the formulas together so you can see some similarities, and just giving a basic description of each one. So let's go ahead and start off with the Fundamental Theorem of Calculus. I'll just label it as FTC, and then the Fundamental Theorem for line integrals on the right hand side. So the formula for Fundamental Theorem of Calculus, obviously we learned that back in Calculus 1, and we've used it so many times by now. So the integral from a to b of f prime of x dx is obviously just going to equal f of b minus f of a. So now the formula for the line integral, for the fundamental theorem for line integrals, is going to be the line integral along C of the dot product of the gradient vector of f and dr is going to equal f of r of b minus f of r of a. So notice the way you evaluate both integrals is very similar. So now the next 2 theorems are going to be Green's theorem and Stokes' theorem. So the formula for Green's theorem, let's say we have the integral along C of some function p times dx plus another function q times dy. Then the formula to evaluate is going to be the double integral described by the region D of the partial derivative of q with respect to x minus the partial derivative of p with respect to y times dA. And then for Stokes' theorem, we have the integral along C of the dot product of the vector field f and dr is going to equal the double integral described by the surface S of the dot product of the curl of f and ds. So for Green's theorem, let's say we have a region D and it's surrounded by the line. If we go ahead and draw a different color, it's surrounded by the line C. So Green's theorem basically relates the line integral along C to the double integral over the region D. Now for Stokes' theorem, it can be thought of as a higher dimensional version of Green's theorem, where instead of the flat region D, we have a surface S. And we also have a line C that sort of covers or surrounds the boundaries of S. So Stokes' theorem basically relates the line integral to the surface integral. So now finally we have the divergence theorem. So the formula for that is going to be the double integral described by the surface S of the dot product of the vector field f and ds. Once again, this is also known as the flux of f across S formula, is going to be equal to the triple integral described by a simple solid region E of the divergence of f times dv. So the divergence theorem just gives another way to evaluate a surface integral or the flux integral by, in this case, taking the triple integral of the divergence of f. So for a final summary, here are all the formulas. So from top to bottom, once again, we have the Fundamental Theorem of Calculus, Fundamental Theorem of Line Integrals, Green's theorem, Stokes' theorem, and finally the Divergence theorem.